Okay, let's get started. So we are going to talk about feature tracking. So on the left-hand side, you see that we are drafting the problems that on the left-hand side, how do we the given image, how do you detect like what are the good corners location that are good for tracking? Yes. No, let's see. It should be there. Let me see. Let me try, see if I can. Okay. All right, sorry, I just update the spreadsheet, so you should be able to download it. All right. Okay, so basically we are going to talk about two things. The first thing is that given an image, how do I determine what are the points that are reliable to track over time? And then once I know where what are the points, and I'm going to track them over time. If the image is moving, I want to know where each key point goes in the future frames, so that I can plot these trajectories. Okay, so and this is the basics for all the virtual reality, all the kind of self-driving cars, or like many different applications. All right. Okay. So imagine that you are trying to kind of align two pictures, right? So the question is about aligning two pictures. And then in this case, we can, so that if I align pictures, and then I can align this into a panorama. But the question is that what are the key points that allows me to do this alignment properly, right? So last time we talked about some pictures are just not good, right? For example, the sky pixel, you don't really know where this pixel where this patch goes in the next frame. And this one, you probably can tell where this what's the motion of the current frame and the next frame if the motion is horizontally. But vertically, you also don't know, right? Because it's slide along the edge. It still looks like an edge, the same edge. So there's some ambiguity there. And only for these type of patches that are good for tracking. Okay, so we talked about this last time. The idea is that we want to define a mathematical quantity that we can compute in a computer so that we can efficiently identify the regions that are good for tracking. Okay, so this just show you that like this is the patches from the current frame, the same patches from the next frame. These are the move patches. So you can see that for the first two columns, you couldn't really tell what the motions is. But the third patches, you can tell exactly what the motion is. Okay, but this is kind of an abstract concept, right? So like it's kind of how do I really define a corner? So we have a precise mathematical formula to describe what does it mean to be easier to track. Okay, so it looks like this. So if I take this patch, and because it's about tracking, so I basically need to know if this patch move a little bit, do I see the arrow, right? Do I see the difference between this patch and the surrounding patches, right? So that's the basic idea, right? So if I have starting with the black box, and if I move to this dash box, and U and V is the motion that move, for example, 3 pixels to the right and 4 pixels to the top. And want to measure the arrows. Basically, what you do is that take these patches, grab the patches from the black box, and grab the patches from the dotted dash box. Then you compute the mean square arrows. Like for every pixel, you compute the difference and square it and sum them all up. All right. So this is the arrows like this. Okay. So if you repeat this for all the possible motion, then you will see something like this, okay? So what you find is that if your hypothetical motion move along the x direction, move to the horizontal direction, you see that the arrow goes up quickly, okay? Which means that it's very easy to locate where this location go. Like horizontal motion is easier, is sensitive to this horizontal motion. But vertical motion, you'll see that they remains small, which means that if I motion along that patch, move vertically, it's not sensitive, okay? Because the arrow, your measure cannot tell how much is moving. So from the sensitivity of how the arrow function goes up, it tells you whether this is easy to track or hard to track, okay? So this is the H part, and you can see from other examples, this one, you can see that all of them are very small, which means that no matter how you move, you give a very small arrow. And which means that you couldn't really tell what are the motions, okay? And on the other hand, you have this patch. You have this patch that is okay. On this patch, you have this one is if you have corners, that is easier to track because no matter what the hypothetical motion you have, you will see large arrow, right? What it means is that no matter what the motion you move, then you will be able to identify the location, what the motion is, okay? That's the basic concept. So let's try to like basically this is EUV, this function is what we want to compute, right? So let's see what that looks like. It's in mathematical formulation, it looks like this. So for XY location within a patch, you look at the corresponding patch in the original image and the shifted patch, and you minus them, you compute the difference, you square them, and you sum them all up, right? Basically, it tells you how similar these two patches are, okay? That's basically the idea. It's an autocorrelation function. All right, so, and we talk about this guy because the U and V is the motion you want to want to compute, but U and V is inside this complicated function of image, right? So what you want is to have a Taylor expansion of that. And the reason why you want to do the approximation is that in order to determine whether a location is easy to track or not, this guy, you want to compute this guy, but this guy is very complicated to compute because you need to basically look at all the possible U and V and then see whether that's good to track or not, right? So it's very, very computation expensive. So what you do is that you apply Taylor expansion. Then what it means is that you in the 1D case, you have this signal. Let's say you have this signal. If I X location, sorry, let's see what is this? Okay, you have this location X at this location, and that you can say Ix is the intensity of that at this location Ix. And what you can do is that, okay, because the image has changes, that's a gradient. And what you can do is that if I X move a little bit, X plus U, and you want to be able to get the Ix plus U, that signal, but you don't want to evaluate that signal directly. But what you can do is that if you know the gradient, that's the change along the X directions, this is the gradient, right? The slope of that change at that Ix location, you can approximate this, right? You can approximate this by saying that you take the Ix plus the U, that's the X shift, times the slope, right? And that is the gradient, right? So U times the gradient of the image along the X direction, And this is the first order Taylor expansion. And this will be valid when your u, that small motion you have, is small, right? Because you have some x square term and cubic term for the following terms. And those terms, because u is small, let's say u is 0.1, then the square term is 0.01, it's getting, and a cube is even smaller, right? So you can easily discard them. So this become a good approximation. Okay, Taylor expansion, yes. So its equation here is that I have a patch at I, and then for every xy locations, I look at the shifted patch, right? I, x plus u, and y plus v is a shifted patch. And basically what I do is to just take these two patches for every location within this window, and I compute the difference, and then sum all the difference up. Yes. Yeah, from the same image. Right. Given image, I want to know is this patch, if I shift this region a little bit, whether that's easy to track or not. The sum is the sum over all the window. Maybe it is a 5x5 window or 7x7 window. Yes. U and V is a function to this things, right? It's a hypothetical motion. Like I don't know what a motion is. Yeah. We don't know what a motion is. But what I want to do, what I want to have is that if this is a good region to track, this guy will be high, will be large, no matter what U and V is. Does it make sense? No matter what the motion is, then which means that it's easy to track, right? It's just another way to say it. Yeah, exactly. So that basically is to say that if this motion, no matter what motion is, it's sensitive to that. It can detect that motion. Yeah, it should be something like this. Like this guy, you can see that it's very small, right? No matter what you move, it's not sensitive. Which means that homogeneous regions like sky patches are not good region to track. Okay, but I need a mathematical formula to be able to help you decide, oh, this is the region to track, right? It's basically this term, the first term. I want to approximate this term, but this is just a 1D case. Yep, exactly. All right. Okay, so this is just say that I can approximate I plus x plus u equal to this term. So a two-dimensional case is also similar. Two-dimensional case is just that you have a xy that the value at that xy location, and plus u times the x derivative and v times the y derivative, right? It's just a simple generalization because image, you can think about image as a 2D function, two-dimensional function. Okay. All right. So if what happened, because you can see now my u and v is outside of this function, so it becomes easier. So now I can just plug this guy into this equation. Then you'll find that ixy and this ixy cancel out. Okay. So if I move this in, this will look like this. Okay. So then I will do maybe some algebra that to simplify this, right? So what I'll do is that this x derivative and y derivative, let's introduce a notation that says that this is ix and iy. Okay. So the square root of this ux plus viy is basically of a plus b and square it. So what is that square? It's just, if you expand this, it's basically ux square, u square, I square, and basically a square plus 2ab plus b square, right? So that's kind of high school math, okay? All right, so, and because you are summing up over the window, what you will do is that it depends on the only thing that depends on the xy location is this Ix, Iy, right? So what you do is does not depend on U and V. The U and V is just a single scalar that tells you what the hypothetical motion is. Right? So which means that you can distribute it into this guy, right? And then you will use some what you learn in freshman year about linear algebra. What you do is that now you can do the following. You can reshape this into this guy. Okay? What's so funny? Is it? Okay, so bring back some fond memory. So, but you can see if you just expand it, it will be the same, right? So it will be the same. Okay, I'm just showing that this guy is the same. It's just a convenient way to write this down. Okay, yeah, you work it out. It should be the same. Okay, so it's a 1/2 times a 2/2 matrix times a 2/1 vector. So it's going to be a scalar, right? It's going to be 1/1. Right? If you look at the dimension, 2/1 times 2/2 times 2/1, it's going to be 1/1. It's going to be a single number. Okay? So what is this thing's doing? This is actually you can think about this. It's a quadratic function, but just like this curve, but it's in 2D, right? It's a 2D quadratic function. And you can characterize this quadratic function by looking at that 2/2 matrix. Okay, so if this 2/2 matrix is then you can characterize this by saying, okay, suppose I have this guy is a constant. Like basically, you can draw the iso curve on that function. Okay, so let's see what that looks like. Okay. So basically, because now you have originally it's from the original equation, you have to compute it, right? You have to compute all the possible location to be able to get that data, the so-called autocorrelation function looks like. You have to literally plug in every different U and V. But now, because that approximation through Taylor expansion, what you can have right now is that for every location, you just need to look at the x gradient and y gradient, come up with that 2/2 matrix. Then you have a two-dimensional quadratic function that approximate these guys. Okay, so what this looks like is the following. So in this case, I'm drawing the curve that where the arrow is constant, is maybe a small number, like maybe the 1. Okay. So this will look like this, all right? So on the left-hand side, what does it mean? It means that I need to move a U and V very far in order to reach some arrow constant. Maybe it's 1, okay? I need to move that a large range in order to reach the arrow. So which means that the arrow curve is very flat. Does it make sense? So that also translates to it's not a good thing to track. Okay, so this guy, you can see if I move the U and V along the x direction, then it's pretty sensitive, right? If you move it a little bit, it quickly reaches that certain arrow, which means that it's sensitive to the x directions for this edge, right? If you move this edge, it's sensitive, but y direction is not sensitive, right? So that you have this kind of this kind of curve. And this guy is very sensitive no matter where you go. Okay? All right. So how do I characterize this? So basically it says that I don't need to look at all the possible U and V. I only need to look at the aggregate x gradient and y gradient in the form of that 2/2 function, 2/2 matrix. Then I know what that arrow shape looks like. So it's an approximation of the actual computation. Okay, and this can be very fast, right? I don't need to, for every location, I look at all the possible motion. I just look at the pixel, look at the gradients around that pixel, then formulate that 2/2 matrix, then I know how to do it. Right? So it's very fast. Okay, so let's assume that there's no x and y gradients. It looks like this, right? So let's say the 2 by 2 matrix is something with A and something with B, and the off diagonal is 0. Okay, so let's build some intuition with some things that kind of simplify example. Okay, so if A and B are 0, basically there's no x gradient and no y gradient. What does that mean? It means that it's a patch with nothing, right? There's no change in x direction, no change in y direction. So it's this one. So obviously this is bad thing to track, right? And what if you have a b equals 0, which means that you have no y gradient, but you have a large a is not 0, so a you have a large x gradient. So you have some changes in the x direction, not changes in the y directions, right? So that looks like this, okay? And what if you have a equals 0? It looks like you have an h, this horizontally, okay, vertically. And what if you have a and b that's larger than 0? It look at this. That's the corner, all right? So now you have now you are able to map this kind of abstract concept or what this mean by a corner to some mathematical formulation. Okay. All right. So in general, you can think about, let's say I plot the arrow iso contour. That's the arrow is constant. So it looks like, in general, it looks like this, right? In this case, it looks like AU plus U squared plus BB squared equals 1. Can anyone tell me what's the equation of this? You probably learned this in high school as well. Also, yes, a circle. Very close. Ellipse, exactly, right? So it's an ellipse equation. Okay, so but usually we don't write in this way, right? We write in this way, right? That's how you kind of you represent ellipse during high school, right? So you have this u squared plus v squared, and you have this this tells you the axis, like a long axis, a small axis, a major or minor axis, to reach the 1. Okay, so it looks like this, and then you can see that A is the minor axis, this guy, and then this guy is the major axis. Okay, so this ellipse tells you this. So if you have a minor axis, it means that you have a fast change, right? If you move along that direction, you will see arrow goes up, like arrow goes to the target very quickly. Okay, if you have this, then this means that it's not sensitive. Right, it's slow change, and fast change is slow changes. Okay, so but in general, we have a 2 by 2. We don't have a diagonal matrix. We have in general we have a full 2 by 2 matrix. So that corresponds to a rotated axis, right? You have a rotated ellipse, right? So you don't. So you have certain. You still have the certain minor axis and large axis, and those minor axis and large axis are given by the eigenvalues of that 2 by 2 matrix. Okay. So what you do, so you have these things, and we talk about the diagonal case, right? But in general, a 2D matrix, can be factorized into a rotation, and you have some eigenvalues in the diagonal and the inverse rotation of this. Okay, so you can factorize any 2D matrix look like this. Okay, and again, these are this guy is the minor axis, and this is a major axis. Okay, so what does it mean to have a corner? What I want to get is that because the major axis is the one who has the slow changes. Okay, the particular direction that will have the slowest changes. And what do I mean by something that's easy to track? Is that I want some regions that even the slowest changes is fast. Okay, that is my definition of something that's easy to track, which means that I want to have that eigenvalues that are smallest eigenvalue in the two eigenvalues that is still large. Okay, I want to have the lambda minima is large. I want to have a large lambda minima. Okay, because that cell tell me that even this axis is not elongated. It's still small. Okay, so what does that look like? So if the corresponding situation is that if both eigenvalues are small, then you have a flat region, right? Basically, like no matter how the motion is, it's all remain flat. And if you have an H, which means that you have a large eigenvalue, basically you are sensitive to one of the directions, but insensitive to the other direction. Okay, so in this case, if you move along the vertical direction, you don't detect that H. Okay, and when you have corners, it means that both the eigenvalues are large. Okay, and so this is exactly how we want to formulate the H corner detection algorithm. We want to see for every location, look at the surrounding gradients. Then you look at the 2x2 matrix, and then see if the minimal eigenvalue is large or not. Then you can take a threshold, and that is your algorithm. Does it make sense? Yes.
So when you just say like max and minimum eigenvalues are large, how do they compare to each other? Because for the edge, you said that max is greater than the minimum.
Yeah, it's much larger than greater. Basically means that in this case, the lambda max tells you that you have some direction that has large changes. Like you have large arrows along, if you move along some direction, in this case, it's horizontal direction. You can clearly identify whether the H is moving horizontally, but you couldn't really locate where the patch go if it moves vertically, right? Or kind of slightly this direction. And that directions correspond to the direction that the arrows that's a minimal eigenvalue. The magnitude that the arrows goes up is because it corresponds to this shape, right? So the minimal eigenvalue, if the minimal eigenvalue is small, then this major axis will be large, which means that you can see that you need to travel long distance in order to see the arrow reach to certain constant. Sense? Any other questions? Okay, so I think it's a good example to see how we can kind of convert something that's very abstract. Let's say I wanted something region good to track to something that's very concrete, and you can compute this on computer. Okay, so now let's see how we actually do this. All right, so you look at the image, like the image here, and the first thing you do is that, by the way, this is important because you need to do this in the homework too. Okay, so you look at this image. Let's say just the intensity. You don't look at the color. It's fine. Then what you do is that you compute the x gradient and y gradient. Okay, so it looks like this. So you look at something that's x gradient and y gradient. Okay, so you can see that they detect vertical changes, this detect horizontal changes, right? And then you look at this. You also have this ix, iy. So which means that you need to compute this guy. Like compute, basically it's just take the So from ix and iy, you need to prepare for every pixel. You need to prepare this 2D matrix, right? And this 2D matrix has three things. One is the ix square, iy squares, and ix, iy. Okay? Make sense? All right, so which means that you can take this and then you can prepare this, right? You can square the the root ix square, iy square, and ix, iy multiplied together. Okay? So now you need to take care of this summation, right? Summation over a window. Can anyone tell me how you can implement this? If I have ix square, how can I compute a summation over a local window. What's that? Mesh grid. Mesh grid only tells you the location of the positions. Okay, so here I have the I square, this is the image, and I want to compute another image where every location is the sum of the local regions for the input image. What is this operation looks like? Yes. Yes, do the convolution. But what is the filter there? Yes. Just once. Yeah. It has a name. No, identity convolution is a filter with only one in the center. Yes, box filter. Yeah. Okay. So this is where the first module come up. All right. So you implement this with box filter, but again, we talk about box filter is not that ideal because they have this frequency problems. So usually, what people would do instead of using this box filter is that they would just use the Gaussian filter instead, right? So you basically say that, okay, instead of just adding up all the pixels intensity within a window, they have a weighted versions, and the weight can use the Gaussian filter. Okay, so which means that you basically are taking these things and then blur it. Okay, so essentially you're taking this and then you blur it. It corresponds to applying a Gaussian filter on top of this ix square, iy square, and iy. Okay, so you have this blur. So now you see that I blur this input, and if I blur it, it gets something like this. It's not that obvious, but you get the idea. Okay, so as we talk about, so now you have for every pixel in this, so you have 3 images, right? For every pixel, you have the corresponding for every pixel, you have 3 numbers, and the 3 numbers correspond to this 2x2 matrix. From that 2x2 matrix, you can compute the eigenvalues, right? So you can compute the eigenvalues. Again, this is a high school, no, probably freshman year. You'll be able to get maxima and minima eigenvalues, right? You basically do the eigen decomposition, and what you see here is that you can see that lambda max, it tells you what is the maximum change of a pixel if I move any arbitrary directions. Okay, and that is basically you can see that it detects some edges, and the minimal change is what we want. Like the minimal eigenvalue is what we want. It tells us like what is the magnitude of change if I move in the least, if I find the least sensitive motion, okay? And this will look like this, okay? And you can see that it's actually, if you take this and then directly threshold it, you'll get something like this, right? If threshold some location, you'll get something like this. But you don't want to keep all the, like for, if I have a pixel that has, that's very like a corner, then surrounding pixels is also very like a corner. So what you do here is you want to suppress the regions that are not the maximum. So basically what you do is that you apply something called non-maximum suppression. Like we talked about this before in the edge detection, but here is a 2D, right? For every location, you look at your neighborhood, and if this pixel, if the value of this pixel is not the maxima of this neighborhood, then you set this to 0. Okay, you suppress something that's not the maximum. And once you did this process, you get okay, you get something like this. It's very difficult to see, but let me show you what that looks like. Okay, you get this picture, and this is basically the location of the corners, right? And this is the key points that you will track over time. Yes. Yeah. You have a 2D matrix, and you do the eigen decomposition to compute that. Yeah, based on the minimal eigenvalue, and you look at the minimal eigenvalue to see. So this is called Shi Tamashi. This is the people who come up with this correlate detection. Basically says that I just look at the minimum of the eigenvalues. If the eigenvalues tells you how the rate change, the change, if the change is if the smallest change is also large, which means that it's very sensitive no matter what direction you are moving, then it's a good corner to detect. Okay, so you look at this, but so you look like this. So basically, lambda 1, lambda 2 is the two eigenvalues, and you can see that they take the minima of them. Okay, the problem here is that it's a little bit costly to compute this, right? Because for every pixel, you need to formulate this you compute this x gradient, y gradient, and then you formulate this 2x2 matrix, and you need to compute this eigenvalues. So at that time, computer is not that fast. So people want to come up with something that's a little bit cheaper, right? So a more popular one is the way to approximate these things. Okay, and so what you do is that you just take there's another two persons that's called Harris and Stephan. What they did is that instead of exactly computing the eigenvalues for every single pixel, what you do is that you just take that matrix A and compute a determinant and then minus some trace square. And it turns out this is a pretty good approximation of the minimal eigenvalues. But here you only need to do simple multiplication, simple operations without the need to compute the actual eigenvalues. Okay, so these are just approximation, right? But you can see that it's a pretty good approximation of the original one. So what you really want is to get something that's the minimal you want to get something that minimal eigenvalues is still large, but you can just compute this matrix, compute these things, and this will give you a number that will indicate that if this guy is large, it also means that the minimal eigenvalue is also large. So it's a good approximation of the original, more complex, more expensive operation. Does it make sense? Okay. Yes. Alpha is a hyperparameters that you can tune, right? So it will tune, if you tune this to certain value. So usually they have a recommended values like 0.6, 0.7. That will indicate that will change how well you can approximate this. But it's not there's no science there, right? So it's just an approximation of because you don't want to compute the eigenvalues directly. Okay, some property about corners. If you look at there's a corner here. Let's think about this. What happens if you rotate it? If I rotate a corner, if I take this image, and if I take a picture, if I rotate a picture, I take another picture, and the corner will rotate, right? Will I still be able to detect the same corner or not? Any idea? So I am taking this, there's a corner, there's a local patch, there's a corner here. And what if I have the image get rotated? Any thoughts? Yes. Yeah.
Unless you know how rotation.
You don't know the rotation, but what I'm asking is that let's say this local patch has certain cornerness score, like maybe I don't know, maybe it's 10. Will the rotation change that cornerness score? Okay. Yes. Yep. Yeah, so if it's in plane rotation, basically only rotate this way, which means that the shape of this 2D things will not change. Okay, which means that it will exactly give you the same rotation. It will give you exactly the same score. So which means that people usually will say that corner detection is invariant to rotation. Okay, so which means that, for example, if I rotate in this way, the 2D shape, because it's basically just a distribution, this is just a summation of the x gradient, y gradient, xy, that correspond to rotating this 2D arrow plot. Okay, the 2x2 matrix. So which means that its rotation is invariant. That is great. How about another type of image changes? What if you have originally you have an image, and then you have some like make it brighter or make it darker? Will this change? Will this have would this change my corner detection? No. The ratio should be the same. It's partially right. So imagine that I have because my image, my corner detection is based on the x gradient and y gradient. If I change the offset, if I change maybe if a whole image I add 50, then that's fine because the x gradient and y gradient are the same. But if I change the scale, maybe I increase the contrast or I decrease the contrast, multiply by 0.5, then it will have different behavior because the x gradient and y gradient will change. So it's invariant to intensity shift, but not invariant to intensity scaling. Okay, so it's partially invariant. All right. So what about scale, right? If I take a picture and then I'm zooming to take another picture, in this case, it will not be invariant at all because in this case, maybe at certain scale, maybe it's far away, it's a corner. But if you zoom in, like say if you have a large scale change, the same corner becomes an edge. So which means that you cannot really, this is not invariant to scale changes. Okay, so there are some these are the major properties about corner detections. Okay, questions so far about this? Yes.
How do you calculate
You use the x gradient filter, right? You use the 0, -1, like -1, 0, 1 for x horizontal, and you of course you want to apply this Gaussian filter, so you have a derivative of Gaussian and use that filter to convolve with your image, then you get an ix, and if you take the filter upside down, then you get an iy. So all these are using the image filters we talk about. Yes. Oh yeah. So intensity shift basically says that, okay, I have an image and I just, for every pixel, I add 20. Okay, that's shift, right? And the reason why it's invariant to intensity shift is because that the quantity that we are trying to measure for cornerness is based on gradient. And gradient essentially is computed difference between images. So it doesn't matter if the both pixels are shifted to the 20, it's the same, right? The difference is the same. Right. So in real world, of course, it's very complex. Sometimes you will have a shift, both shift and scaling, right? Maybe your exposure is have higher contrast, then you are basically stretching the thing, and that will change the gradient. So which means that maybe for this image, you will detect a corner, but maybe if you kind of do some post-processing, maybe you don't detect it. Okay, or the other way around. Maybe you didn't detect in this image, but after you have certain contrast, you detect it. Okay, but the basic idea is that because that you are using the gradient to capture this property. Okay. All right, so now we know how we identify the location where that's good to track. Now we need to actually track it over time. All right, so let's see how that looks like. So imagine that you have some motion in the things like this case. It's that's the hand of this motion, and let's see how we can track this motion. Okay, so let's look at this. So I have two images. Image one, t, and image t plus one. And let's zoom into a local regions. Okay, so zoom into a local regions. And so what we want to know is that, okay, the tip of his hand at this location, I want to know where that point go. What's the motion of this point in the next frame? Okay, and because it's not there, it's not at the original position, there's an offset. I want to figure out what is the offset that move this point to the next frame. And this tells you the motion, right? This tells you how things move. Okay. And again, we talk about, I think last time we talked about, if you can figure out the motion of pixels, you figure out a lot of things, right? You figure out the spatial temporal structures, you figure out how the dynamic objects is moving in your video, right? So this is the problem of feature tracking. And that feature tracking, you have so many different applications. Yeah, you are able to do, if you can track the videos, like how the video frames moving, you can do video stabilization. You can stabilize the video because you can shift your frames so that you compensate the motion. You can do object tracking. You can, okay, I have a suspect that's running, and you can track them over time. Right? You know where they're going. You can do motion analysis. Maybe, I don't know, you have Parkinson patients, you need to understand their gait, you need to analyze their motions over time, or SLAM system where you want to know where your robot is or your drone is in the environment. You need to know where that where that camera is with respect to the environment. So for that, you need to track the key points around the scene and be able to localize your position. All right, so this is the foundation of many, many different applications. So, but let's see how we can actually do this. Basically, the problem is that given XY locations at that point, how do I know where that point go in the future frames? Okay, so to solve this problem, we have some assumptions. We first need to assume that this point, the color or the intensity of that pixel you want to track does not change from the next to the next frame. Okay, this is called brightness constancy, because if everything is changing, you don't have any basis to track, right? So you need to make some assumption that the pixel at this location and in the next frame, the color stay the same. Imagine if I change color, then you have no way to track. So that's the assumption, basic assumption you make. So to make this assumption, what does that look like mathematically? It looks like this, okay? So it means that the XY location at time t, the intensity of that pixel is the same intensity of the x plus u and y plus v at time t plus 1, okay? This is just says that the pixel you want to track does not change color, does not change brightness. Okay, that's a math to describe what I just said. All right. Yes.
If you were to do something like where we normalize the floating frame t to t plus 1,
yeah,
would that change like the accuracy of the?
Yeah. So this algorithm rely on the basic algorithm we were trying to describe relies on the assumption. But if the assumption is violated, then you will decrease the accuracy. For example, which means that it's very difficult to track the object. For example, if I'm walking in the direct sunlight and I walk into something that's shadow, then the pixel on top of me will be difficult to track. For there, you need to develop some other algorithm. I think last time we talked about some NVIDIA research, they highlight this kind of challenges, right? If you look into the sun, a lot of pixels are saturated and they have some dynamic range, then how do you track along that direction? That's There are more research in order to solve this problem. But the baseline is this. Okay. Okay. So brightness constancy is the number one things we can do. And another assumption is that we cannot really solve for this if we don't make certain assumption. In this case, the second assumption we made is that we assume the motion is small, okay? Because it's a video, right? So it's video from one frame to another. I couldn't from this frame move to suddenly to very far away, right? So it must be some continuous change. So I assume that the motion that is a u and v, they are small, okay? So in order to do analysis, you can see that u and v here, they live inside that complicated image function, okay? Can anyone tell me what are the tricks to move them out? We just used that trick before. If the u and v are small, how can we move that u and v out of this complicated function? It's a famous singer. Taylor expansion, right? If the u and v is small, then you can approximate this guy into this guy, right? So it's the same thing, right? So you have, if I at this location, then you have three gradients right now, right? You have a x gradient along the x direction, y direction, and time directions, okay? So you have the x derivative, y derivative, and t derivative, time derivative. That is the next frame minus the current frame. Okay, so with these two assumptions, we can now formulate an equation, right? We know that this guy is the same, right? So what we do is that we just plug in this guy and plugging this guy into this guy, all right? So similarly, you see that this guy and this guy, the IXYT and IXYT, they are live on the both side, left-hand side and right-hand side, right? So you cancel them out, then you know there's an equation, a 1D equation like this, okay? So now, again, the job we want to get is to figure out what u and v is, right? We need to know what u and v is. So if I have an equation, what does that mean? Like in this case, it's an equation. It's not just an equation, it's a linear equation of u and v, which means that I have, let's say the solution is this guy, and what the equation tells us is that there's a line pass through that u and v, okay? But I don't know what exactly u and v is because every point on that line satisfy that equation. There's the ambiguity here, okay? So we are a dilemma, right? So because every pixel we look at, you only give if I look at a single pixel, that I need to figure out the motion that is u and v, that's two numbers. I have two unknowns, but the u and v tell me only the one equation. So I cannot solve a system of equation with one equation, but two unknowns. There's ambiguity here, right? So can anyone tell me how you could solve it? How could you solve for two unknowns? If you solve the linear algebra, you have two unknowns, but you only have one equation right now. How can you solve it? Any ideas? Fundamentally, you cannot just look at this equation and solve it, right? Because that equation only tells you a line, and all the points on that line satisfy that equation. But how do you actually pinpoint the actual equation, actual solution? Yes.
You can try different points on the line.
Try different points on the line, but all the points on the line satisfy that equation will just go to zero. It satisfies your constraint. All that those are possible motion. Yes. So we have two unknowns in this case. Differential equation. How do you do this? I do have two unknowns, but I only have one equation right now. So the question is, how do I solve this? Yes.
We basically just like a matrix or something like that of unknowns.
Yeah. So right now we have two unknowns. But right now we only have, if I only look at one equation, 1 point, I only have one equation. Yes. Okay, so multiple reference point. Basically, it's very, very close. So the idea is that I have two unknowns. I only have one equation, and in order to solve this, I just need to get more equations, right? That's a basic idea. But how do I get more equations? Yes. Another friend, but then it's not this motion, right? It's not. I'm looking at this particular kind of tip of the hand, like the XY. That is what we are interested in. How do I get more equations? Oh, what's that? Another friend? Another point on from. Okay, that is correct. So, which means that there's a fundamental assumption that we want to make. That is, I want to make the spatial coherence, which means that, like if I have a point that moves a certain way, then the surrounding point also moves similarly. So I can borrow the equation from nearby pixels. Okay? Does it make sense? So I can borrow information from nearby pixel. So, and I make assumption, I assume that they have the same motion. Okay? What it means is that initially I only have one equation and I want to solve two unknowns. So I couldn't really solve it, right? In this case. So what I would do is that maybe I look at, in this case, I look at a 3x3 patch. Okay? If a 3x3 patch, then I will be able to, for the pixel on the top left, I also have the ix, iy, and minus it, right? So, but I assume that they share the same u and v, okay? The same motion. But I assume that it kind of makes sense, right? If I have a patch here, I have a point here, the nearby point should move similarly, right? It's not randomly moving, okay? So it means that I can borrow equation from nearby point, and now give me, in this case, n points, n equations. All right. So now, if you look at this, how do you actually solve it? Like I have a linear, sequence, a collection of equations. What should I solve it? Like what are the steps? In this case, like we have been doing the same algorithm many times. Can you say that again? Yeah, this is a system. This is called a system of linear equation, right? What are the steps to address this? I reverse identify unknown, right? Yeah. So I need to. These are unknown. And I basically move the unknown into a column vector, and the right of say basically whatever we do is essentially I want to rewrite this into a form of ax equal b, and then I can use the linear least square solution to solve this. Okay, so it's kind of we have a tool to solving a problem. Then what we need to do is essentially to map whatever we observe into that form, and then we can solve it. We can use a tool. That's basically the idea. So in this case, we have this linear system equation. And I know that this unknown, that's u and v. Then what I do is that I just do the reshuffling like this. Okay, I move the u and v, the column vector, and you can see this is exactly the same thing. Let me show this again. u and v, each equation is u and v, then what I do is that I formulate this, okay? So now I have columns, number of rows, that's n, like in this case it's a 9, and 9 by 2 matrix, and the u and v is 2 by 1, and in this case on the right hand side is 9 by 1, okay? So now you have a d equals b, okay? So this is called an over-determinate system. Okay, it's that you don't have a unique, so it's overly determined system because you have more equation than your unknowns, right? Imagine you have two lines, two equation, then you can easily figure out the intersection, right? That's your solution to both equation. Okay, that's how like your high school is taught. But now you have more equations than your unknowns, which means that in the 2D plot, you actually have many equations, many lines. And what you want to do is to find a point that minimizes most of them. Like you couldn't exactly pinpoint that. So you need a least square solution. Okay? The way you solve the least square is to multiply this, the A transpose on both sides, and then you get something like this. Okay? So this should remind you what the matrix looks like. This is exactly the 2 by 2 matrix we just talked about, right? This is exactly the matrix we just talked about, that IA square, IY square, and IX IY, okay? And in order to be able to solve for this 2 by 2 and 2 by 1 and 2 by 1 system of equation, what is the condition that we can solve it? If I have a matrix multiplied by this, they equal that. What do I need to know before I know I can get this solution? Any ideas? Yes. Exactly. If this is invertible, all right. So this also relates to so if it is, let's say if it is invertible, then I can write this. Okay, that's my solution. Okay, so if you look at this thing, and what does it mean by invertible? Like if you, let's say if both eigenvalues, if this is a smooth patch, if this is a smooth patch, then all the eigenvalues are close to 0. Would that be invertible? If I have a matrix, they're all 0, right? Because x gradient and y gradient are very small. Then it means that it's not invertible, right? You couldn't invert this, and therefore you couldn't figure out a motion. So this is another way to look at whether a patch is good to track, right? And earlier we said that if both the eigenvalues are large, even the smallest eigenvalue are large, which means that when you invert this, you will be able to get a stable solution. Okay, and this is why you want to identify the patches that are not just the corner, but also that implies that is something that you can actually compute the motion. Okay, so both are related. Okay, so what the algorithm looks like? So you have this xy, and again, similarly, you take this frame and then compute the x gradient. Look like this. This is you apply a gradient filter, apply to all the location. You have an h gradient, and you have a y gradient like this, and you have a t gradient. That's the difference between these two frames, and you get this. You get this. Oh, sorry. You get this. All right. So now you have ax, iy, and it. All right. So what's the next step? What you do is that you take ix square, iy square, and ix iy for every locations. Okay. So it's not pretty very good visualized, but you get the idea. For every location, you have this 2 by 2 matrix. Okay. On the right hand side, you have this ix it and iy it. It is just element-wise multiplications. So similarly, you do the summation. You replace the summation as a Gaussian filter. You just convolve a Gaussian filter. So with that, you have everything you need. for this location, you have all the this linear system equation. You have this 2 by 2 matrix. It's just a ix square, iy, and this guy, and then iy square, right? So you have all the things you need to formulate this. So every pixel, you have the same equation. You have this equation. Okay, every pixel you can formulate these equations. So what you do is that you can solve for the u and v what the motion actually is by taking a least square solution of this. Questions so far? So you can see that how they use the simple linear algebra and make some assumption and be able to solve the problem. Okay, make sense? All right, so but the story does not end here. There are still problems. Okay, so what are the problems? The first problem is that because we make the assumption that u and v are small, this only works when u and v are small. So which means that you cannot get to the solution immediately, right? So because if your u and v, that your motion is slightly larger, this solution does not give you the actual answer in one shot. So what you do, the idea to fix this is that you can apply the same algorithm multiple times to get to the solution. So here, this is the idea of iterative refinement. So we need 2 ideas to solve this, to solve for larger motion. Okay, the first idea is iterative refinement. What this looks like is that initially I don't know where the pixel go, right? So I just assume that the initial motion is 0, 0. Basically, assume that nothing moves. Okay, and then once I do that, I know the corresponding pixel is just x prime y prime that doesn't move in this case, and then we can compute the IT, the difference, temporal difference between the new pixel and the old pixel, right? That is the difference between at location x prime y prime minus xy. Again, initially, u and v are initialized to be 0, so which means that it's like this frame and this frame, and the corresponding pixel, you just take this pixel minus this pixel, the temporal difference. All right, and once you have this IT, you compute this motion, u and v, you get a motion from this equation, and then, but the interesting thing is that now you have a rough idea of where the motion actually is. You move toward that directions, u and v, which means that you can update the ix, update this guy, right? You know where the pixel is. Now you have a better initialization than previous step, all right? So which means that you get the update your x plot, y plot, that's the corresponding pixel in the next frame. Then you compute the IT and then estimate motion again. So you basically apply the same least square solution multiple times, like say usually 10 times, so that you can iteratively converge to the right motion. Okay, so this is the iterative first idea of iterative refinement. Question about this? Okay, so basically is that my algorithm only works when the motion u and v are small. But what if u, v are large? And the idea is that, okay, I still assume that they are small, but I just iteratively solve it, right? I just, every time I make some progress and I move to a new location and then make some more progress, okay? So that's the main idea, iterative refinement. The second idea is called coarse to fine, okay? So it looks like this. Okay, it looks like this. So imagine that in this example, there's like large motion, right? Because this is a high resolution image, and then like the motion is very large. The main idea is the following. So remember that we talk about, I think Yao Zi talked about the pyramid, okay? So if you have a large motion in the high resolution, and let's say if you construct a Gaussian pyramid for each image, what you do is that you get something lower and lower resolution, okay? So now you look at the coarse resolution. There any large motion, if you have a large motion, let's say 10 pixels in the high resolution, but if you go down 1/16, then it becomes 1/10/16 pixel motion, right? Because everything is just a few pixels only. So what you do is that instead of trying to find the actual motion in the original resolution, you first downsample it so that they are tiny images. And any large motion in the high resolution image becomes tiny motion in the low resolution image. So that is basically kind of coarse to fine estimation. So what you do is the following. It's very simple. You start from the lowest resolution. Now you want to estimate from XY to estimate the corresponding location in X plane, Y plane, right? So what you do, initially you don't know what that is, so you assume that XY is X plane, Y plane is the same as XY. So you run this called iterative Lucas-Conate algorithm, run this multiple times, you get the estimated motion. I say, okay, certain motion, the UV, and now you can update the correspondence. That this XY is this guy, okay? And now what you do is that you upsample the solution, right? Because this is the very tiny image, and if you make the image 2 times larger, you just update your solution to be 2 times larger, okay? That's very simple, right? And then you try to, now you have a good initialization, okay? Better initialization in the next stage. Now you look at the level 3, now your XY, X plane, Y plane is not the same location of XY. It's the solution coming from the previous stage, okay? So now you can see that it's already pretty accurate. And at this level, you only need to correct, you figured out what the tiny offset is. And this is where the Lucas-Conate algorithm will work. Okay, and then you move on and then move to the next one. You solve this again, and you just repeat this, right? You start from a coarse resolution, solve a coarse solution, upsample the solution, and then refine it. Okay, refine it, and all the way to the top solution. Okay, and that's basically it. So the main idea is that you have this assumption, you assume that the motion, the brightness is constant, and you assume that the motion is small, and the nearby pixel moves similarly. From these 3 assumptions, you derive how you could solve for the unknown motion for every pixels, U and V. But the problem is that this only works when you have small motion. And therefore, for real world cases, what you need to do is to make anything that's large motion into something small motion, right? The way you do this, first idea is to iteratively apply the same algorithm. And the second idea is that because it's large motion in the high resolution image, it becomes small motion in the low resolution image. And therefore, you can do this coarse to fine estimation. You can apply the algorithm that's working in the small motion can be applied to this. Okay, and it's a very simple idea, but it has a large impact on everything, all the application we see today. Okay, sorry for missing 1 minute. So I'll talk with you this Thursday. Thanks.